Well, hello everybody. My name is Oscar Leong, and today I would like to discuss with you a bit about my research I conducted last semester in regards to a result in combinatorial geometry known as Helly's theorem. So in 1913, Edward Helly formalized a statement about the intersection of a finite family of complex sets in any dimension. So just to put all that in English, basically a complex set is a collection of points which can draw a line between any two points. So a couple of simple examples will be a square, a circle, or a triangle. So Helly's theorem states that in two dimensions, if we have any number of complex sets greater than 2, and every 3 of them have a point in common, that means they all must have at least one point in common. So here on the slide I have an example of Helly's theorem in 2 dimensions with 4 complex sets. So the diagram on the left shows every possible combination of 3 out of the 4 complex sets, and the red area is their common points. And on the right, if we put all the complex sets back together, we see that they have common points, which is also shown in red. So this satisfies Helly's theorem in 2 dimensions. But it turns out that if you have any number of complex sets, as long as an intersection condition holds, then Helly's theorem holds true. So if you have 10 complex sets and every 3 of them have a point in common, they all have a point in common. Even if you have 100 complex sets and every 3 of them have a point in common, then they all have a point in common. And Helly's theorem actually generalizes to higher dimensions as well. And so in my research, I focused on Helly's theorem but for different types of sets. So I focused on what are known as unions of complex sets. So we can think of a union of complex sets as gluing 2 or more complex sets together to create a new set. So a nice illustrative example would be an L shape. So you can think of an L as gluing together a horizontal rectangle and a vertical rectangle, and now you get a new set that's not necessarily complex. And it turns out to be a number of Helly theorems for that, which use tools from topology, computational geometry, and linear programming. But aside from these results, my research led me to a very interesting discovery. Ever since the formalization of Helly's theorem in 1913, there have been a number of generalizations and variants known as Helly-type theorems. And a Helly-type theorem is formulated as follows. If every n members of a family of objects have a particular property T, then the entire family of objects has this property T. And in a recent survey of Helly-type theorems, there turns out to be over 50 different theorems of this type of formulation, spanning over 5 different areas of mathematics. Now I find this like a result to be incredibly astounding for the following reason. One of the beautiful things that I appreciate about Helly's theorem is how simply and effectively it's communicated. That's a common phrase. All we have to do is see if a property holds for a subset of family of objects, and we hope, and it turns out to be true, that it ends up working out for all objects itself. So what we're really doing is a very human and logical process. We're trying to see if a pattern arises in nature. Hopefully that will generalize to our natural world so we can understand our own world that much better. So to me, mathematics seems so natural as it elegantly coincides with our own human intuition. So with this in mind, I want to leave you with this. The next time you think about or look at mathematics, look past the 2-dimensional shapes and figures, but to appreciate the underlying human element that encompasses mathematics as a whole.